Chapter 12, Part 4, Imines, Enamines, and Reductive Amination. So this is continuing in the trend of nucleophilic addition to carbonyl carbons. And this is what happens when you have a nucleophilic addition of a primary or secondary amine. So let's first introduce these new functional groups. So first up we have our imine. An imine is formed when a ketone or aldehyde reacts with a primary amine in acid. And we can identify an imine by noticing that we have what essentially looks like a carbonyl, but with a nitrogen on it instead. So this actually would have been our carbonyl carbon. So whatever our carbonyl was, in this case it would have been a ketone, it was here. And this would be the structure of our primary amine. Now one thing you want to notice is that a primary amine is going to have the format of NH2 with an R group on it. Notice that there are no hydrogens on this nitrogen anymore because the bonds that would have been made to hydrogen are now actually made to carbon. So an imine is a nitrogen with a double bond to carbon and a single bond to another carbon. An enamine is one of my favorite things. It is a celebrity couple name because we have an amine and an alkene touching the same carbon. Now again, this comes from the reaction of a carbonyl with an amine. This would be our carbonyl carbon. This is the secondary amine that would have done this reaction. And these are formed when a ketone or aldehyde reacts with a secondary amine in acid, giving us an enamine. Now, the mechanism of formation of an enamine and imine are actually very similar. The entire first half is essentially identical, and then the enamine ends up branching off because we end up not being able to deprotonate a key intermediate in the way that we would deprotonate it in the formation of the imine. So I'll show you when we look at the mechanism coming up in a second. But drawing out an enamine is not as complicated as it seems. You would have had some sort of ketone or aldehyde here, and you're essentially just going to be deprotonating the alpha carbon. The structure of this will make a little more sense as we work our way through it. But an enamine, again, is easy to spot because you're going to have an amine attached to the same carbon that is part of an alkene as well, enamine. So let's take a look at the mechanism of the formation of an imine. So this mechanism is going to look almost obnoxiously familiar because we just did this when we were looking at the formation of acetals. It only varies at the very end because what you'll notice is that with an acetal, we were adding 2 equivalents of an alcohol, but with the formation of an imine or an enamine, we're only adding once. So there's only 1 equivalent of the amine ending up in the product. But I want to go ahead and do a little color coding so you can see where these atoms are coming from and where they end up. So here are the carbons of your ketone. Here they are in the product. Here are the carbons of your amine. And here they are in the product. And once again, our carbonyl oxygen ends up being lost as water. So that gives us a really, really big hint as to how this mechanism occurs. So let's take a look at this. This is going to start off very, very similarly to what we saw in the previous mechanism, we are in acid. So the first thing we want to do is protonate the ketone. Now, is the ketone the strongest base in this? Absolutely not. The amine is a much, much stronger base. But this is the only protonation that moves us forward in the reaction. So this is the only one that we need to worry about. Remember, proton on, proton off, all that stuff is in equilibrium. So protons are just being moved around all the time. So this puts a positive charge on the oxygen. And again, this is resonance stabilized, which helps us see why this is an important step, right? We can see now that we've created a much, much better electrophile here than we would have had without the protonation. So at this point, the amine is going to attack. So amine attacks here, that pushes up the electrons onto the oxygen, or you're welcome to draw the resonance form and show the amine attacking there. It doesn't matter, you're going to end up in the same place, no matter how you draw it. So what we end up with is a hydroxyl group attached to the same carbon as a nitrogen that now has way too many things on it. So just like in our last mechanism, we now have a species that needs to be deprotonated. So let's deprotonate it. We have other amines in the mixture floating around, or maybe another ketone. Something is going to deprotonate this. Let's go ahead and use the amine because it's more likely, just because it's a better base. Okay, so now we're here. Now, if we want to get rid of this hydroxyl group and lose an equivalent of water, we're going to have to protonate it and turn it into an equivalent of water. So we need to pick up a proton. Sorry to draw that kind of far away because of my other structures in the way. Okay, so now we can show the water leaving. You could even show the amine kicking it out if you wanted. A lot of people do. It's not really necessary. I'm trying to keep it looking similar to what you've seen before. So this gives us this intermediate here, which looks really, really familiar. This is what we had right after we had the hemiacetal. And actually, I forgot to throw in the fun word over here. When you're halfway to an imine, this is called a hemiaminal. So halfway to an imine is called an hemiaminal. So at this point, we actually do have to draw a resonance form in order to get us to our next helpful structure. So if we draw the resonance form of this, actually let me draw that up because I don't really have space to the side. We'll see that the resonance form is actually very, very close to our product. It just has one extra proton that we don't want. So we can remove that. We can either use the water that we made, or we can use an amine floating around. But that gets us to our final product, the imine. So what's really cool about this mechanism is just like the formation of the acetal, it is fully reversible. So if we want to get rid of an imine, turn it back into our starting materials of carbonyl compound and amine, all we have to do is add in an excess of water and a source of acid, and Le Chatelier's principle is going to do the work for us. And again, just like with the hydrolysis of an acetal, the mechanism is exactly the opposite of what we just did. So our last step here was to deprotonate to get to the imine. Our first step of going back towards the ketone and amine is going to be to protonate on this nitrogen using that lone pair. And then we could draw a resonance form that looks like this, or we could just have water attack over here to get us here. And then we just keep moving forward by reversing everything we just did. So the process of adding water and acid to get back to here would again be called hydrolysis. Lots of parallels between the chemistry of amines and acetals. So the mechanism for the formation of enamines is very, very similar, but it does branch off at one particular point, and it's because we kind of reach a point where we get stuck. So I'm going to kind of speed through everything we just did because we already saw it, but I want you to understand where these structures came from. So we're going to start by protonating. And we know that there's a useful resonance form here, but I'm going to go ahead and jump into attacking this guy. Pushing the electrons up onto the oxygen. So this gets me almost to that hemi-ami now. So this time I'm going to have a hydrogen attached, I'm going to have a methyl group, and I have an ethyl group, all in this one, nitrogen, which does not have a lone pair anymore. It has a positive charge. So I need to deprotonate this before I can move forward. I'm going to use another equivalent of the amine to accomplish that. So I have my hemi-ami now. And I want to get rid of that oxygen. So I'm going to do the same thing I did last time. I'm going to protonate it and turn it into water, our better leaving group. So then water is able to leave. And I find myself here. Now last time we did a resonance form, and then we deprotonated our amine and we were at our imine. This time what we're going to find is that our nitrogen is again positively charged, but not because it has an extra proton. It's because it has an extra bond. And we're not able to deprotonate this nitrogen to make it happy, but we also don't want to get stuck here. This is called an iminium. So kind of like how ammonia is called ammonium when it's protonated, and an amine is also called an ammonium when it's protonated. An imine, when it has a positive charge, is called an iminium ion. And we do not want to leave that charge on the nitrogen. We want to fix it. But there's no way to fix it from up here. So we're going to pull a trick from beta elimination here. And we're going to pull off a proton from our neighboring beta carbon, or well, alpha carbon in this case. We haven't talked about alpha carbons and carbonyls yet, but we will shortly. So water or another amine could come along and pull off this proton, which forms a double bond. Actually, let me color code so these are easier to see. Forms a double bond, and that pushes the electrons up onto the nitrogen, which ultimately gives it its lone pair back. And this is also how we get that double bond. So that's where the ene part of the enamine comes from. It's because we get stuck at the iminium ion and we're not able to directly deprotonate the nitrogen. So we end up having to deprotonate nearby and push those electrons towards the nitrogen. Now you might be wondering, why can't I deprotonate from here? Go ahead and draw out on your paper what would happen if you did do that. Now, if you took a second and maybe you paused, or if you didn't, maybe pause now, you might have drawn a couple different interesting things. If you did pull off that proton, you would create a double bond between the nitrogen and that carbon, which could leave you with something like this, which has a whole lot going on. That nitrogen is currently sporting 5 bonds. That's very bizarre. Something else you could have done would be to actually continue to push these pi electrons down, which would give you something maybe even a little more bizarre, where you have a nitrogen. It's still positively charged at this point because it has 4 bonds, but now you also have a negative charge on what was your carbonyl carbon. So basically, this is just not the direction that you can push electrons in. You want to push electrons through an atom that is already sp2 hybridized. That is a helpful thing towards the source of the positive charge. So that is why we are not going to pull off the proton next to the nitrogen. We're going to pull one off from next to the carbonyl. Okay, so at the end of chapter 10, our chapter on amines, we talked through a concept of why we do not use amines to do substitution chemistry in order to make secondary and tertiary amines. And the answer to that was basically you're going to end up with a mess of products, and it's pretty difficult to control. You have to use like a massive excess of one thing or another, and then you just can't be as selective as you could be using this process, reductive amination. So this is a process to selectively synthesize secondary and tertiary amines. And what I've done here is I've outlined the process for you. So you're going to take a ketone or an aldehyde. And if you react it with a primary amine, you're going to make an imine. If you react it with a secondary amine, that's going to get you to an enamine. Either way, you're then going to reduce that imine or enamine using a combination of hydrogen gas and a transition metal. So it could be nickel, it could be palladium over carbon, and that's going to give you a secondary or tertiary amine. So let's take a look at an example. So if I take a ketone or an aldehyde, in this case a ketone, and I react it with a primary amine, that is going to give me an imine. This imine is then able to be reduced using hydrogen gas and a transition metal. Now notice this double bond is behaving just like the double bond of a ketone or an aldehyde. It is able to be reduced, which is actually something we're going to talk about at the end of this chapter. We've also seen alkenes being reduced in this way before. So this is not new chemistry, we're just applying it differently. So this double bond, we're adding a hydrogen to the nitrogen, we're also adding a hydrogen to the carbon. So this is the same type of reduction chemistry we've seen before, and this gives us a secondary amine that we had control over the formation of. Now again, if you take a ketone or an aldehyde and react with the secondary amine, you're going to form an enamine. You're going to get rid of that double bond via reduction, and that would give you a tertiary amine. Same process, just maybe fancier outcome. So let's take a look at a practice problem. Go ahead and pause it and see if you can come up with the products of step 1 and then step 2. So what I'd like to do is help you rush through the product formation. I don't want you to have to draw out the entire mechanism just to figure out what's going to happen. So let's talk through this. Now, as always, I want you to identify that carbonyl carbon because that is the carbon that the nitrogen is going to become attached to. And I also want you to take a look at your amine and decide, is this primary or secondary? This amine is secondary. So our product of step 1 should be an enamine, not an imine. So I'm going to draw out my carbon framework. I'm going to go ahead and draw that hydrogen in just to keep track so that the shape continues to look familiar to me. And then I'm going to attach my nitrogen. Now, if I were drawing an imine, it would be really simple. I would just draw that double bond right there and I would be done. But my product is going to be an enamine, so it's not as simple. I have to look at my carbonyl carbon and decide to deprotonate from my nearby alpha carbon. Now, I can't deprotonate from this side because that's an aldehydic carbon, hydrogen, and that is directly attached to the carbonyl carbon. That is not where I want to deprotonate from. I want to deprotonate from nearby, immediately next door. So this is the one I'm going to pull off. So let's go ahead and let's just draw out this step of the mechanism just so we're clear. I'm going to erase that lone pair, put a positive charge on there and a double bond. So this step of the mechanism, let's go ahead and I'm just going to shorthand it with B- because I don't want to take up too much space on this page. And I'm going to pull off this proton. That's going to make a double bond here. And that is going to break this double bond and give those electrons to the nitrogen. So my product after step 1 is an enamine that looks like this. Now, if you didn't need to draw this to get there, awesome. I love that for you. If you did need a little extra support to understand where that double bond comes from, that's what I was aiming for. Personally, what I'd really like you to be able to do is just plop the amine on there and then deciding whether it's an imine or an enamine, figure out if you need a double bond here or here. But that takes practice, and you just learned this 5 minutes ago, so we're not quite there yet. And then this is our product after step 1. And then in step 2, we're taking this and reacting it with hydrogen and palladium on carbon, one of our reducing agents that we learned back in chapter 5 when we were doing alkene chemistry. This is going to add hydrogens to each of these alkene carbons. So this is my final product. Now, if you wanted to draw this a little more nicely, putting things like in a row, that would be like this. And you wouldn't need to draw this aldehydic proton anymore. It's just a regular hydrogen on a carbon at this point. It lives here on this molecule, but we don't need it. So this is our final product. This is likely what it would look like on a quiz or an exam. I'm less likely to draw it like this, where the main chain is not really in line, but anyway, that's reductive amination.